Okay, so in the next question, um, we're asked to think about gibbons. Gibbons are a type of monkey, or related to monkeys, and they're one of the best brachiators in the world, according to what I've read. Um, and that means that they swing from tree limb to tree limb using their arms. They have very long arms, and they suspend their masses as they do so. And we're told that the top speed of a gibbon is something like 55 kilometers per hour. And if we assume that they reach this at the bottom of their swing, we're asked to figure out what the force on the gibbon, the force that the gibbon exerts on a tree limb is at this point. And so if we think about an object that's swinging from an arm, it would start out with perhaps its arm reaching the tree in one direction, and it would swing forward. It would be fastest at the bottom of its swing, and then as it starts to release on one location, it will put out its other arm to try to go to the next tree. So we're going to assume that this gibbon can be modeled as though it's a point mass hanging at the bottom of a mostly massless arm. So we're right at the point where it's vertical, and we're told that our gibbon has a speed of 55 kilometers per hour, which seems really high, but apparently that's the kind of speed that these are able to reach to. And we notice the type of motion that this gibbon has looks a lot like the problem that we had in class where we were walking and our hip was going through a circular motion. Here it looks like the arm of the gibbon is the length of an object, and the body of the gibbon is going through circular motion. So this is a problem in circular dynamics, and at the location that we're interested in, we know that there's a force that the gibbon's exerting on the tree limb, and the force that the tree limb is exerting on the gibbon should be equal to that. So force of the tree on gibbon equals force of the gibbon on tree. And this will act like a tension force in this problem. The gibbon, of course, is pulling down on the tree, but the tree is pulling up on the gibbon. So if we draw a free body diagram for this problem, we have our x direction is pointing upwards towards the tree. That's the direction that our acceleration is to remain in circular motion. Our net force we would expect to be upwards then, so that we have this gibbon in circular motion. Might put a y-axis there, put a dot to represent our gibbon. Our gibbon has a weight of the gibbon, and our gibbon also has something like a tension force, which we're calling force of the tree on the gibbon. So if we can solve for this force of the tree on the gibbon, that should be equal to the force of the gibbon on the tree by Newton's third law. So this is a problem in circular dynamics. And in circular dynamics, we know that there's a relationship between the speed of our object and its centripetal acceleration. We are not given our speed in meters per second, so we'd like to convert this. The conversion from kilometers per hour to meters per second is 3.6. And so 55 divided by 3.6 gives us 15.2 or 15.3 meters per second. And it's useful to have our things in SI units at the start of a problem. Then the sum of the forces in the x direction is equal to the force that the tree puts on the gibbon. That's in the positive x direction. The weight of the gibbon is in the negative x direction. This should be equal to the mass times the acceleration along that x direction, which is the speed of the gibbon squared, divided by the radius of the gibbon. And so the speed and the mass, these are things that we know. So this is 7 kilograms. The speed of the gibbon is 15.3 meters per second. And the radius of the gibbon's arm, so we're assuming our gibbon is point-like except for their long arm, is equal to 0.9. The weight of the gibbon is 7 kilograms times 9.8 meters per second squared. And so the force that the tree puts on the gibbon is the weight of the gibbon, 7 times 9.8 newtons, plus 7 times 15.3 squared divided by 0.9. And those are all in SI units, so we bring back in our calculator. 7 times 9.8 plus 7 times 15.3 squared divided by 0.9 equals, and this comes to 1889 newtons. And then we look at our answers, and 1889 to two significant figures rounds up to 1900 newtons. And so because the force of the gibbon on the tree is equal to the force of the tree on the gibbon, the force of the tree on the gibbon being 1900 newtons, the force of the gibbon acting on the tree is 1900 newtons as well.